Thank you for coming. My name is Imran. Um, I'm a GDE in machine learning and also a machine learning software engineer at Compo Group Medical. So today we're going to talk about attention in AI, attention mechanism particularly. Um, so I'll show you what the contents are. So these are the topics we're going to cover. The last two topics are going to be more of a discussion rather than information. Um, and before I move even further, I'm going to go back into the chat room and ask a question. How many of you are familiar with machine learning, or any or the any of admin? If you have any idea about it, please let me know. Like 80% are students or professionals, or what's the scenario here? So I don't spend so much time on the beginning. You can write in the chat. I can try and read that.
Uh, I am newcomer to it, Imran.
Okay. So even if there is just one newcomer, I'm going to assume that some of you are. So I'll try and make things easy. The slides are going to be very long. There's so many slides, but I'll try and skim through the ones that are not so important, at least in my eyes, right? Um, okay. So let's first start with basically uh, the idea of machine learning, right? So forget machine learning for now. Consider this: you have a an input called Celsius degree, right? Which is a temperature, and you wanted to convert it to Fahrenheit degree, right? In this scenario, what do you have? You have in the non in things in this scenario are the Celsius input, right, and the function f, right, and you can compute the Fahrenheit degree from these two, right? So you have the input and you have the function, and from these two you can compute the output, right? This is called determinism or deterministic programming, right? So input, you have a function, you give this function your input and you receive an output. This is normal programming, right? Now we try and understand how machine learning evolves from it, right? Some of the times you know the input and you also know the output, right? So for example, you have a lot of data, and this data include images of horse or cat. The example I gave you is a very simple example. And you also know what each of this image actually is, right? So you do actually know if it's an image of a horse or if it's an image of a cat, right? So you call that that non-entity as label, right? um and what you know in this scenario is you know the input, you know the output, but you don't know the function, right? So if I ask you what's the formula of converting image of a horse or a cat into a label, either a horse or a cat, then there is no specific formula for that. Or even if there is one, we don't know it yet, right? And it certainly won't be any simple formula like the one we saw here, the simple one, right? So we're going to assume that there is a formula or there is a function, right? And the idea of machine learning is essentially we need to approximate this entity, this function f, right? Sorry, this function f is basically what we're trying to optimize. And the way we do that is um, we compare the prediction to the actual label, and the way we find it is how far we are from our actual output is how we optimize, right? So This is essentially how machine learning works in a very higher level, in a very simplistic manner, right? Um, okay. So, mm, okay. So this entails that you know at least what features are, right? This slide. I know this isn't exactly for the machine learning beginners, like someone who's probably never had a class, but I'll try to give you a, a small understanding of what a feature is. A feature is basically an input, right? So the input can be divided into multiple parts. Um, one input can be one feature, or input can be one feature, or it could have multiple features, right? So we treat pixels of an image as features, right? And these pixels, they look like a matrix. Actually, they look more like a tensor, because at each point in this matrix, so let's say this x11 will have a three uh, array value or a four array value, right? So which corresponds to red, green, blue, and if it's the transparent image, then it's also alpha, right? Mm. So what we're going to do is basically in machine learning. So in this example, we had the input image of a horse or a cat. Um, as and we treat this image as basically a matrix, and each point in the matrix we're going to consider as a feature, right? So we will have x and m number of features here, right? Assuming this is a grayscale image and these are not tensors, these are just simple matrices, which means that there's just one value of x11 and not RGB values, right? By the way, I forgot to mention that I would like to treat this presentation as more of a conversation, right? So you have a question in between, ask away, or at least use the chat room, Google Meet chat. So I know if something's not clear and maybe I'm moving too fast or moving too slow, please let me know. There's so many slides, but let's try and focus. Let's try and learn. Yeah, right. So I'll go to the chat room from time to time and see if there's any question right now. Right, there's none right now. I'll move forward. And if you think anything is unclear, please let me know. Mm. So until now, we have seen that um, when we have numeric features, things are much easier, right? So these pixels, they can be treated as decimal values or maybe even integer values if you're dealing with ranges from 0 to 255. But yeah, assume that they're just decimal values, right? And computer or a machine knows how to deal with decimal values, right? It knows how to deal with floating points. um so you can multiply a floating point with some weight value and add some other value to it, right? And then you can also perform other um operations on it, right? But this is not the same case with the natural language, right? um they don't The machines don't understand the words directly, right? So I've given this example here. My name is Imran can be defined in infinite number of ways, right? It could be defined as a single decimal point. It could be defined as a one hot encoded vector like 101, or it could be defined as any arbitrary n size of a vector, 0 1 2 3 4 or 0 1 2 3 4 5 or 1 0 2 3 4, infinite number of possibilities, right? um so even before we move to how we optimize this function for a natural language, we've seen that in natural language we have a problem even before that, which is we need to uh, basically convert this input sequence of words into uh, uh, into maybe a fixed size vector or a value, right? So the machine can actually process it. It knows that one means cat or zero means whatever, right? So there's an added problem even before selecting the image, right? So, uh, so natural language is particularly harder than and um images of maybe some other type of data, which is in the form of nice matrices and everything.
Okay. Imran, what is meant by natural language?
My natural language is maybe another any language like English, Urdu,
Okay.
Hindi, right?
Mhm.
Um, and the way so in this example, the input is an image, right? And the
Yeah.
images could be this image, right? This
Yeah.
image
Yeah.
basically translates to a matrix of decimals or a matrix of tensors, right? So we already
Mhm.
have numerical values. But when I say my name is Imran, which is a natural language sentence, right? Um, they what does my mean, right? A machine does not know that. Does it mean zero? Does it mean one? Does it mean 0.54627? What does that mean, right? Um, so there's an added problem. We need to convert this sentence or this document or this sequence into a fixed vector so the machine can actually start processing it, right?
Yeah. Mhm.
I hope it makes sense.
Okay. Vector is mean by zero and one. Is in a combination of zero and one, zero
Uh,
and ones.
so a vector does not necessarily have to have only zeros and ones. It could have like something like this: 0, 1, 2, 3, 4, right? A vector is basically consider a vector like an array, right? An array can have n length, and it can have um, unique or non-unique uh, a number of numbers, basically numbers, integers, decimals, whatever, right?
Okay. Mhm.
Okay,
Yeah. Okay. Thank you.
okay. And this is an example of why language is also hard, right? So I've imagine this. In this scenario, I'll go back to this picture. The pixels around the face of the horse, they they actually start to make sense. The continuity of them starts to make sense, right? So if you take, I'm not really sure if I can point towards it. Wait, let me see if I can. Yeah. So this part, if we take this part only of the horse, right? This part makes sense, right? So the pixels from here and the pixels from here will make sense because they are in a continuous manner, right? Which means that um, um, they might look exactly the same, or they might look a lot similar to each other, right? And this is a good thing. This is a good thing for machine learning because machine learning can now start making sense of these local features. um, this is not exactly the same in language, right? In language you will have not local relationship, but you will have a global perspective, right? So a sentence might only start making sense at the end of it, or the emotion of the sentence could change entirely, right? And I will give you an example in the next slide. So the first sentence is, I am ashamed of my friend because he's always a better person than I am. If I only look at the first part of the sentence, then it produces a negative emotion, right? But if I take the entirety of this sentence, then I know that it is a positive emotion and it's talking about something positive, right? And there's another example, right? And this example is basically one word could have multiple meanings depending on the context, right? So I am near the bank of the river versus I went to the bank for some work, right? Now the bank here is basically the same word for both sentences, but the way it's used, it basically changes the context. So or I can say the words around it change the context of this word, right? So these are actually a very really hard problems, and you will see in the future slides, it's it takes a lot of time to basically counter these problems, right? And global context changes emotion, right? Which is this. So this is, so if this is the local context. Local context is I am ashamed of my friend, right? Um, this is a local context. But if I complete the sentence, I'm ashamed of my friend because he's a better person than I am, then it's a global context, and the global context is entirely different from what we saw earlier. And word orderings changes meaning entirely. Yeah. Another different difficult issue in languages, in language type machine learning models, is in typically machine learning prefers, or the vanilla machine learning, I wouldn't say vanilla, even the modern machine learning, it's based on input that is fixed, right? So a machine learning model might expect an input of 10 features, let's say, right? And the training and the prediction, it would always be 10 features, right? So 10, let's say, 10. So if I want to predict the price of a house, let's say the model is predict the price of the house given 10 properties of the house. These 10 properties are the 10 features, right? And I want to predict the price of the house. So this 10 properties, they're fixed, right? But in language, it cannot be fixed. So a sentence, so let's say I give you an example, right? uh, Given a sentence or given a sequence of word, produce an emotion, right? Or predict an emotion. Is this a negative emotion sentence, or is this angry, or is this positive or happy or whatever, right? So the sentence could be of multiple length. One sentence could be very long, one sentence could be I am angry, right? Just three letters. And one could be an entire paragraph of why I'm so happy today, right? So this is also another added issue, that the input can have multiple, or can have a wider range of input. The input can have a wider range of words, sorry, or tokens. I'll explain what tokens are. And another, because I mentioned here that you also need global context. And for global context, you actually need memory, right? So this is an example. The book that professor recommended last Thursday was really good. When you're processing this particular input really good, you need to know that we're talking about the book. We're not talking about Thursday, we're talking about the book. So the machine learning model somehow needs to adjust or make some memory for this word as well, the book, right? Mm, right. Um, so even before we begin or move towards this function f, which are the algorithms for machine learning in the context of natural language, right? Um, we have another added problem, like I said. So we need to convert these sentences, this the book that professor recommends last Thursday was really good, into a fixed vector, right? So the machine learning algorithm can process it. And this is basically done via these algorithms uh, that basically converts them. They're not called Virtu numbers. This is just an arbitrary name I've given to the slide. But basically, these are the algorithms that make your natural language sentences or your documents. Uh, they make them into a format where where you can feed it to an optimization algorithm, right? Or a machine learning algorithm. Um, yeah. Mm, Hopefully the code is visible here. I just copy pasted from my VS Code, and I did not realize that it would not look good um on the Google slide. Anyone can confirm if this is readable or not? The black part here.
Yes, it is readable.
Okay, thank you.
Yeah.
Uh, okay, awesome. So one easy way and the one historical way how people used to do it was this algorithm called one-hot encoding, right? It basically converts a word into a unique vector, and this unique vector basically is a binary um, a binary array, right? So if you have these unique words in your corpus or in your training data, right? Cat, dog, mouse, run. So each of these word will get a unique value, a unique binary value, right? So the the run would be assigned the value 1, mouse 2, dog 3, and cat 4 all in the binary, right? So each of this word in this corpus, they get a unique value. And in this code base, this is basically a pseudo code base, right? It's not an actual code, but this is how it works, right? So you go through all the unique words in your vocabulary. A vocabulary is basically a set of unique words in all your documents, right? So for the sake of simplicity, let's assume that in our scenario that we only had 4 unique letters in our document, right? Cat, dog, mouse, and run. So we go through these 4 words and we generate a new binary encoding for them, and this is and you basically save it to this database called word2vector, and where the key is the actual word and the binary encoding is the value for this, right? And this is how basically um, for every word and where you need to feed it to a machine learning algorithm, you would convert it into a one-hot encoding vector and then feed it. And this is a very old way and historical way of doing things. It's one-hot encoding is still used, but not for the same purpose anymore. And
So,
yeah, yes,
so
yes,
in the machine learning model in the background uses natural language, and which converts into the vector. That's the understanding is
yes,
correct.
yes, yes, that is correct.
Yeah, yeah. Okay, then thank you.
All right. And one-hot encoding has multiple problems, right? Um, so you can see here, how would you know a dog is more similar to a cat than a mouse, right? Because it needs to make sense. It needs to, so a queen is a woman and a king is a man, right? This needs to make sense. And I will show you why. Run is similar to running, right? But the model does not know that. The model only knows that run is 0001 and maybe the running is 01010, right? So there's no, you cannot compare these two. So if I take the distance between dog and cat, it could be that it's more than the distance between dog and mouse or dog and run, which is not nice, right? So you need this similarity. In the case of images, you already have that, right? So you know that these pixels, a pixel from here will be very much similar to a pixel from here, right? So there you already have a local um, relationship. But here, when we convert them into these binary vectors or these unique vectors, you don't have this relationship between two almost identical entities, right? So you need a sort of way to basically make these embeddings or make these vectors in such a way that they give you the right uh, spatial understanding. Spatial understanding basically means a dog in in a higher dimension would be similar to a cat than a mouse. And this is basically solved by this another technique, which so there are a lot of techniques in between, but I'm going to skip through them. I'm just going to focus on the more one, the more that are used today, right? Um, so word embeddings, the next technique after one-hot encoding. So here you can see that if we plot these vectors on, let's say, maybe a 3D scale, we can see that a woman is nearer to a queen and a mother, and a king is near to a man and a father, or maybe an uncle, right? And this makes sense, right? um, because this is exactly what we want. And this is basically how the word embeddings look like. So they're not now, they're still unique, right? But they're not um, some binary values, right? Now similar words are closer together, right? So relationship now start to make sense. So if you have a vector of a king and you subtract the vector of a man from it and you add a vector from a woman, you will get an almost identical embedding of a queen. So this is basically semantic understanding that we have introduced now, right? And and it's very simple to produce. You basically just train a neural network that takes an input word and tries to predict the next one. I also have added the pseudocode for how it works, right? So the first part actually looks similar. You create the word to vect, which is the one hot encoding that we created earlier, and then you create the training data for this neural network, right? So training data is basically input word, and the output would be the next word in the document, right? So the next word is the word plus one. So basically the input is the one hot encoding of the current word, and the label then would be the one hot encoding of the word that came after it, right? And this is how you create this entire training data. And once this training data is created, you train a small neural network on it, right? Or I mean, it could be a larger one, but let's assume for the sake of simplicity a small neural network, right? And once you train it, you get the you so once you train it, you have this thing called an embedding or hidden layer inside. So let's say it's this neural network had input layer, a small middle layer, or the embedding layer in between, and then the final layer. So what you do is once you've trained the model, you use this middle embedding layer as a type of as a type of representation for your input, right? This representation could be, um, mm, how would I say it? Mm, could be used instead of the one hot encoding vector. And since you have trained from this input to output, this hidden embedding starts to make sense, right? So this hidden layer, it starts to make sense. Um, I mean, this is the sort of the higher level idea of word embeddings, right? But there's still one problem. I am near the bank of the river, and I went to the bank for some work. It still doesn't solve that. The reason it still doesn't solve that is because the bank in the both scenarios will have the same embedding because they are in the same corpus, right? Maybe they're in the same corpus when we were training this neural network. So the bank, and since it's just a lookup, the bank will have the same embedding, and we still wouldn't be able to figure out what type of bank is it talking about, right? Everything clear up until now. Okay, I'm going to assume yes. Um, I'm going to now move from, okay, so now we've covered, we will not begin starting to discuss this function f in case of natural language machine learning, right? So we will just converted our sequence of words into an input that can be into an input that is valid for a machine learning algorithm, right? So we've just converted this input yet. Now we're going to see the 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 models itself, right? And these models and there's a sequence to how they basically come, right? In the very start you had the RNNs, and then you had the LSTMs, TMs, gate recurrent units, sequence to sequence models, and then you basically from these models you went to the attention. I will give you a small, a very minute overview of what each model look like, except for the sequence to sequence, because that is very important for our attention mechanism. And so basically give you a historical evidence of what happened, uh, why it did not work, why we moved to a better option, and how we moved to it, right? So let's start with the most basic one, rn. It's a very old model. um, the actual theory behind it is even from the 40s, Markovian chains. not 40s, but not 40s actually, but very old, right? Anyways, so what recurrent networks does is basically they maintain a hidden state, like, right? So I told you in natural language you need to maintain a history, right? So what they do is they maintain a hidden state. So every word in a sentence, so let's say the sentence was the cat said, right? So the D here would be x1, the first input, and it will produce a hidden output called h1, right? And the 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 next word cat will produce a hidden output called h2, and the the set the word set will produce a hidden output called s3. So we are now maintaining, excuse me, we are now maintaining a set of hidden states, right? So we remember the word the, even when we're at the end of the sentence, right? So the sentence my name is Imran, when we're at the end of it, the system should remember the word my is still there, right? Not someone else is talking about me, my name, right? And this is basically the function for it. It looks pretty simple. So the input at given time t, it takes the hidden state of the previous uh, word, right? So im name, the word name will take the hidden state of the word my and produce its hidden state, and the word is going to take the the hidden state of name and produce its hidden state, right? And the same way the word Imran is going to take the hidden state of is and then produce its hidden state, right? So you're basically maintaining a memory here. Now this is just a very high level overview. This is obviously not exactly how they work, but the higher level overview of how they work, right? And there's a problem with recurrent neural networks, right? So if you have a longer sequence, right? So imagine you have a, instead of just this sentence called my name is Imran, you have this entire document of, let's say, 500 words, right? Or maybe 20 sentences. Then what happens is, in recurrent neural networks, when you go further in the sentence or you go further in the word in the word sequence, right? When you add the, maybe the end of the file or maybe the end of a sentence, you start losing context from the very beginning of the sentence or maybe from the very beginning of the documents. And this happens through this technical problem called vanishing gradients, right? um I'm not going to go into the very detail of it, but in this optimization algorithms, there's this thing called back propagation, right? And back propagation is basically how you learn these weights and these biases, uh, right? And what happens is you take a partial derivatives of your function, right? And when you take a partial derivative of these hidden chains or these longer chains, the chains in the very end, they start to lose their gradient. They start to have a very minute effect, which is equivalent to zero. Actually, in theory, and not in theory, technically it can go equivalent to zero. And we know this because we know the activation function behind it, and we cannot help avoid it, right? um I know this is a very higher level understanding of what why this problem occurred, but again, a recurrent neural networks, LSTMs, they're not part of the discussion right now, and I'm not going to focus a lot on them. But I really hope you understand um how RNNs work on a higher level, right? And what problem they pose, right? Um, so they were not good, and so then some researchers, they made some improvement on recurrent neural networks, and we called them the long short-term memory and the gated recurrent neuron. The gated recurrent neurons came very long after the LSTMs, um, but the idea was essentially the same. So what happens in an RNN is you made in hidden states, right? And the problem was vanishing gradients, right? So the words in the start of the sentence or in the start of the sequence, um, um, the RNN would tend to forget them, right? So the LSTM, it basically introduced a method of gating, right? So the gating is basically in information flow, the control of information flow, and basically the idea was the gates would help us basically remember what parts to the gates would help us see what parts to remember and what parts to forget. So um in a longer document, I'm not I don't have an example in mind, but in a longer document it would only focus on the parts that need not to be forgotten, right? um so the gradients not basically squash in back propagation, right? Yeah, so this is the idea of LSTMs. There's still again still the same problem occurred. I mean, even though it solved the vanishing gradient problems, but even at very long sequences, maybe um, I don't exactly know what very long means, but maybe let's say, let's for the sake of argument take 500 words as a very long sequence. It This LSTM and G are used to still fit, right? And they were very slow because of the computation gates. Okay, and then we found a really nice method to basically solve all this. And they're called the sequence to sequence models. They solve the longer sequence and uses encoder decoder architecture, which was a big innovation. And it was nothing new basically. It was basically having all the components that were previously there and just combining them together to make a something that is really nice, right? And this is basically how it works. So you have an input sentence, you put it through an encoder, you create this thing called context vector. I will explain further what a context vector is. And then the decoder, it takes the context vector and produces an output sentence. It was usually used in translation purposes. So I've given a rough pseudocode of how it works, right? I did not write it in the Visual Studio. I just wrote the pseudocode here. So the input is a cat sat and we want to translate it to Urdu एक बिल्ली बैठ गई, ठीक है? All right. Um, so the way how it works is basically, so you have the input, right? You have input a cat set. You tokenize the input, right? Oh, by the way, when I say word embeddings, right, in the modern form, in the modern large language models or transformers, you don't use the vanilla word embeddings. You use something called tokenized uh, tokenized positional embeddings, right? I'll explain further what that is, but let's, for the sake of simplicity, um, and a lot of things here, for the sake of simplicity, they're not followed as is. There's a lot of delta on top, but this is the basic backbone of how it works, right? So you have an input, right? A cat set, and you convert it, and you basically tokenize it, cat and set. Sorry. Um, and then what you do is for each of the word, you generate the embeddings, the token embeddings or the word embeddings that we talked about earlier, right? The technique that is still used today. And then the encoder encodes the vectors with an RNN. So the encoder is basically a machine learning model, right? It takes these word embeddings as inputs, and it's basically an RNN. Okay, so the RNN is also arbitrary. It in more practical cases, it's either an LSTM or a gated recurrent unit. But for the sake of simplicity, I added recurrent networks because even in the vanilla part of sec to sec, the actual thing was, I think, RNN. But for the sake of simplicity, let's just assume it's an RN because it doesn't really make sense to add more complexity here when we're just trying to understand the basics. Um, so the encoder, it encodes the word embeddings uh, with a recurrent word map, right? The way it does that is uh, mm, it takes the input let's say it takes the first part, the x1. X1 is basically the word embeddings of the. Okay, I read it here actually. So the word embeddings of the are passed through this RNN to create the first hidden state, right? The h0 is initially random, so I didn't write it, and from this you create the next hidden state for the cat h2, and then from the h2 you create the third hidden state for the word set, right? And this the cat set is, I'm talking about these word embeddings here, not that the actual language words, right? um and then once you went through all these tokens or these words, you reach this state called end of sentence or end, right? It's usually written with a end, right? This or this, right? And once you reach the end of the sentence or the end of the sequence, in the part of the encoder, it stops. Now the last hidden state, h3 in our case, will become the context vector, which means the decoder will take this final hidden state or this h3 vector and consider it as an input, right? So the decoder, it will now start generating the translation, the Urdu translation for it, right? um so as a first part, so it's going to start uh when it's going to start, sorry, it's going to take the first input as a token called start, right? And then the context vector, yes.
Yeah, where these encoders and decoders are present, are these present in the ML models or natural language models? So where these encoders are present actually?
So this encoder is essentially a machine learning model in itself, right?
Each
And
okay, how many models we have machine learning models, and what is the naming convention of it, and where we come to know that these are the machine learning models we have it? Do we have any documentation about it?
okay, so a machine learning model is basically um I'm not really sure how to explain it, but this is essentially a bunch of functions packed together that are optimized through this process called backpropagation, right? So any approximation of function packaged with backpropagation is could be called a machine learning model, right? Um, an encoder is one part of this machine learning model. Is one type, sorry, one type of this machine learning model. Decoder is also one type of this machine learning model, right?
Okay, yeah, thank you, understood.
Okay. Um, and then the decoder basically starts taking the context vector, which was the last hidden state of the the last hidden state of the encoder model, right? Um, so this is the context vector from encoder. And now it also has its own recurrent neural network. So H1 would be basically X0, which is the start token, and the H0, which is the context vector from the encoder state. And then the decoder produces a probability function. It's basically another layer of another layer in the neural network. It produces the next token, right? The next token in our case would be zero point 0.8, the one with the highest probability, which is called egg, right? And now this egg or will be fed back to the to this recurrent neural network, where the the hidden state would be the hidden state of egg, right? And the input would be the oh sorry, the input would be x1. X1 in our case would be egg, and the hidden state would now and now we use the hidden state of the previous one, which is the h1, to produce the h2, right? And the next one it would say is called Billy, and it will start keep producing it until it sees the end of the token called end. These end and start tokens may be different. They may be sometimes used like SOS start of sentence or EOS end of sentence, but it doesn't really matter. This is very important, right? Because this serves as the foundation for attention models. Mm. In practice, um, doesn't use the last predicted word in training. Um, it uses the actual label. What does it mean is that when you're basically going through this word by word in the decoder part, the decoder does not, in the training process, it does not take the predicted word as the input uh, or as the input to the next hidden state. It actually uses the actual label while training, but this is not important right now. Even with sec to sec, it had a lot of problems, right? A long documents, maybe 5,000 words, it would still wouldn't work. Um, Another big problem is that all this input, this is a small input anyways. If this is was a 5,000 word input, this 5,000 word input context would be jammed up in just one hidden state, the last hidden state, which is not good. So you would actually lose a lot of context jamming all of this 5,000 word document into this just one small hidden state, right? So that was a problem. Um, and this would basically again cause early information to disappear, right? So you have not exactly 2 minutes, but just a few seconds to tell me, given this sequence to sequence problems, how would you suggest to basically fix it? Any idea? This is the line that we need to fix actually. Okay, the way you can fix it is, instead of looking at the final hidden layer, instead of looking at H3 only, you look at H1, H2, and H3 and decide which one to use. And this deciding part is called attention. This is as simple as that. So it's just a sequence to sequence model. Instead, now you just have one small lookup where instead of using the H3, you use either one of H1, H2, or H3, or until H1 and 2 in a real world, right? And that's it basically. So input sentence goes to the encoder, right? This, I don't think this is the correct form. The encoder, generates multiple hidden states like it did earlier. uh, the decoder selects the best state, right? It does not necessarily have to select the H3 state. It can select the best state. Again, I will try and explain how it works, right? So again, you have the same example, a cat sat, and I want to translate it into ek billi baith ki Urdu, and you generate the token embeddings, the cat sat. Again, you with the encoder, you produce these three hidden cells, right? H1, H2, and H3, hidden states, sorry. And now, um, and the decoder step, it starts to get a little different than before, right? So the decoder starts generating output, right? So it creates this thing called H0, which was also done earlier, and now the H1 takes the hidden state and the X0. The X0 again in our case would be the start, this SOS or start a token. So it knows that the decoder has started. And what you do again, what you do different this time is that you create this thing called query. A query is basically a weight times the h1. This is essentially a learnable parameter, and the weight are learnable. They're parameters. They're not hyperparameters. And you basically, once you create that, you create similarity between the h1 of the encoder with the h2 of the encoder, with first hidden, second hidden, third hidden state of the encoder. You basically compute the similarity. So what does the input most correspond with? Does it correspond with hidden state 1, hidden state 2, or hidden state 3? In simpler words, what does the first output uh, l- so what does the first output basically is similar to? Is it similar to the cat or sat, right? So you have this three scores. You normalize those scores with softmax. Softmax basically is a function that takes the values and jams up into them to probabilities with sum up to one, right? Um, and then from these weights, you create a context vector. So now instead of using the last hidden state of the encoder, you use all the hidden states of the encoder, but you assign weights to it, right? So maybe the cat had the highest weight, so it will produce the maximum amount of enforcement in the context vector, right? And this enforcement would be controlled or scaled with these weights that we created through softmax from the similarity metric, right? A similarity metric could be anything, could be cosine similarity or anything, or a dot product in some case, right? And then after that, it's the same, right? You generate um, the output word through this okay. And then what you do is you basically, instead of now only using the hidden state one, you now concatenate this context vector into this hidden state to produce the next word called ek, and then you repeat this step four again. Oh, sorry, not six, step four. This should be four. Okay, until you reach the end of token. So now essentially what's different is that we've introduced this smart context vector. This smart context vector is basically a combination of all the hidden states of encoder scaled by their weight. So maybe uh, if the input needed to focus more on the instead of cat and sat, this would have a higher weight, right? And this is basically how a vanilla attention layer works, right? So now we've established how basically what a sec to sec model does, how attention is added to this sec to sec model, and now we're going to see even a better form of this attention model, right? Which is the more widely used form of attention. And this widely used form of attention is basically uses this key value pair, query key value pair, right? We also said q key qkv, qkv. Um, and it's a more sophisticated form of moving forward, right? I will explain to you what query key and value are in this example. So now we have the same example. English is a cat sat, Urdu is ek billi bat gayi, right? Um, you tokenize the input, again the same thing. You generate the word embeddings or the token embeddings, and then you say encoder encodes the vector with RNN. Excuse me. So this step is also the same. So you generate three hidden states with RNN of the embedder, right? Of the sorry encoder. And furthermore, you generate two more things. You generate the keys and then you generate the values. Keys are basically the weights times the hidden state one, weight times all the hidden states, right? And you have then the three number of keys depending on the sequence, the number of sequence, the number of tokens in the sequence or the words. And the same way you generate these values in the sequence. So each token will get a value, right? And these are learnable parameters because these w's and these these w's, they are learnable parameters. So you basically train them while doing backpropagation. And I will explain further what keys and values actually mean in this context. um, and then this decoder, it's again the starts the same, initially random. The h1 is the first decoder hidden state is generated, and then instead of creating, in like in this case, creating the context vectors from the very start, we create something called a mm, mm, okay, we actually do that, but we instead of doing it directly, we use these attention scores, right? So how we do that is basically we create the query. So query is another learnable parameter uh, with WQ, but we already had that in the vanilla form. So you have the WQ times the first hidden state, you get the first Q1, right? And then you what you do is you compute the attention scores. Again, this could be um, dot product, cosine similarity. In our case, we use the dot product. So instead of just if you remember here, we used the similarity between the query and the encoder of the hidden state, the first hidden state of encoder. Now what we're doing is basically we're computing attention scores not with the hidden states but with the keys of the hidden state, right? The keys of the k1, k2, and the keys of the hidden state for our decoder first step q1. And then what you do is you normalize. Again, you pass them through the softmax, and then what you do is you generate the context vector. The context vector in this case is now weights times the value, which was also a learnable parameter. And once you generate this context vector, then you basically again concatenate this context vector into your h1 decoder, which is this thing, and you combine them, generate the next word, and then you start this step again from the six, right, until you reach the end of token or the end. This is a lot to take, and the basically I will explain to you why QKV method is better than vanilla method, right? It basically separates the responsibilities. The way it separates the responsibilities is that the keys are now used only for searching in the hidden states or in the encoder state, and the values are basically the information buckets where we get the information from, right? So you separate the concerns. Once you separate the concerns, it's easier for you to train, and you can actually get more context out of it because now the concerns are separate, right? And um, one also good reason for doing that is now you have a wider space, spatially you have more um, flexibility to represent a word. All right. um, I hope it makes sense. um, the Kuke-Fao method also allows for self-attention, a technique that lets each token form a relationship with another token. So self-attention again is mm, is a problem, or is a model that tries to solve this problem that we saw earlier. I am near the bank of the river versus I went to the bank of for some work, right? In this case, the self-attention will try and basically solve it, right? So it will try and check the relationship of one token or one word to all rest of the other words in the sentence and form a context. So previously we had fixed embeddings, right? The only had this embedding, cat had this, sad had that, sad had this embedding, right? And it will remain the same. But in self-retention, the way you do that is these embeddings, the embedding of the word bank here and the embedding of the word bank here will be different. And this is basically the idea of self-retention, right? Is it so the idea is each word is influenced by other words in the same sentence or in the same sequence. Um, Again, this helps clarify meaning. Okay, for self attention to work, simple word embeddings don't usually work. Use potential, like I said earlier. But for the sake of simplicity, I'm going to work with word embeddings for now. So this is basically how it works. Let's quickly go through them. Right, the animal did not cross the street because it was tired. This is the input sentence. Now the word it is, if you look at it without the context, you don't know what it is. But we know in this context, we're talking about the animal, right? So what you do first is you convert these words into vectors. These vectors are basically the word embeddings, right? The word embedding animal didn't cross the street because it was tired. So you create 10 embeddings, right? And then you create key value pairs. So the uh, key value pairs, sorry. For every word, you have a qi, a q, a k, and a v, right? And they're learnable parameters. They're weights actually. They're used with weights, and sometimes there's also bias here. But let's, for the sake of simplicity, don't talk about bias here. Um, So, and now you compare query with all keys. So you basically search this query among all the keys to basically get a score metric, right? So you get a score for one word. Let's say the word was it. You get a score for all the other words with it, right? So it had, let's say, a score of 0.1 with was, 0.2 with because, and maybe zero point 0.9 or 0.7 with animal, right? So you get a score, and then you basically normalize the scores, right? So after, even just after normalizing, you can get this added sum up to 1. um and then you build a new representation, right? A new representation is basically sum of all the attention of this ij times the value, uh, in the value, which is this one, right? So now the word it has a different embedding than it previously had. Now it will not have x8, it will have maybe, let's say, x8 index, which is more similar to animal than maybe was, right? And this is basically how you prepare self attention in a con in a in a sequence. um What if we use self-attention in our QKV sec to sec? This was our QKV attention model, which was a sec to sec, sequence to sequence. What if instead of attention, we use self-attention here, right? And once we use self-attention in QKV sequence to sequence, it's called transformers model, right? Um, and again, I tried to basically write down the steps of these transformer models, but I think it's easier to explain it via this image, right? So previously what we had was, we had this thing called encoder, and we had this thing called decoder, right? um and the encoder would encode this sequence of words, right? And this sequence of word would then form a context vector, which was used in decoder, right? Now what we do is instead of producing the context vector first, it tries and produce the query key value pairs in the encoder part to basically make sense of the input. So the bank, in the I am near the bank and I am at the bank for the loan. Now the bank embeddings in this encoder are different, right? For both of the sequences. So we have a self-attention layer here, right? And then we also have a self-attention layer in decoder, right? And once you have these two self-attention layers, there's another attention layer on top of them, which is this one. And this is also also a self-attention layer when you basically combine the decoder and encoder based on the context vector and the hidden states of sorry, not just the context vector, right? And there's this thing called multi-head self-attention. Multi-head self-attention means there's not just one query key value pair. There are maybe n number of query key value pair, usually 8 or 16. Um, and the idea behind multi-head self-attention is uh, each each self-attention focuses on a different problem, right? So let's say in language, one self-attention would be focusing more on the grammar, one self-attention would be focusing more on the context, one self-attention would be focusing more, let's say, on the general structure of the sentence, right? Mm. And the key components are self-attention, right? Feed-forward layers. Feed-forward layers are the basic fully connected layers. Layer normalization, residual connection. A residual connection is something that we did not talk about. It's a it's being used in transformer from the very start, but I thought it would be very too much detail right now. And then positional encoding. Positional encoding is basically word embeddings plus um, mm, sorry, token embeddings plus their positional encodings, right? And transformer basically process entire sequences simultaneously. This is not important. It's not important. And basically, just like I said, the multi-head attention, one could be focus. There are multi-head attention, self-attention mechanism, right? In encoder and decoder. So maybe one's head focus on positional relationship, one semantic relationship, and one grammatical structures. And multiple perspective, when they're combined together, they form the final result. Um, this is basically the major part of my uh, of the technical, the major technical part. And now the question is why attention works and why transformers are so powerful, right? And I would like to basically direct this towards the audience. Why do you think the attention works, and why do you think the transformers are so powerful?
Based on attentions, we get the score, right? So that we can validate it based upon
Based on, can you repeat again?
attention gives score, right?
Attention used
Gives score.
scores. Yeah.
Based on that, we can find out the relevance between the tokens. Relevance between the tokens.
That is correct actually. So the idea behind attention is self-attention itself is that if you have a sequence of words, if you have a sentence, then one word in the sequence will have a relationship with the rest of the words, right? And this
Yeah.
relationship is scaled by weights, which is essentially what you're talking about, right? So this is
Yeah.
essentially why attention works. And now to talk about why transformers are so powerful, there's two main reasons. One reason is this multi-head attention layer, which is basically you learn multiple things in one go, in one architecture. And the other good thing is transformers layers are made in such a way that you can parallelize a lot of stuff. And this is why you see there's such a boom in large language models right now, right? Um, Mm, because they can be paralyzed while training, and this is really nice. The last part of this in this presentation focuses on basically what are the applications of transformers, right? So the biggest application of transformer is large language models, which is basically, for example, ChatGPT, but Gemini or stuff like this, right? And the again it's used almost in everywhere. I think you would know this more than me. And yeah, I think this is sort of it. Thank you.
Uh, Thank you, Imran, for your session. Yeah, thanks a lot.
Yeah.
And one question I
Thank you,
have is,
Imran, bhai.
Yeah, I have one question.
Mm-hmm.
Uh, so Google has a vector. Google has Vertex AI or in a Gemini Enterprise, right?
Mm-hmm.
And if you see, the Vertex AI contains a large model content where you can see and a lot of models are present.
Mm-hmm.
We can consume those models and we can leverage it, right, to do our day-to-day operations or to experiment anything. Uh, so that can be a much more easy for the customers to utilize the current existing things which are present
Mm-hmm.
instead of developing all these things. So as a beginner, so what you suggested for us to learn quickly and to experiment with the things and go with the flow of the technology.
I think Google Cloud also provides. I'm not really sure about the link, but it provides a very fast and learnable way of getting started with the um, with the practical part of it, right? You don't really need to know the attention mechanism or self attention or transformers in general. You just need to basically get started with these Gemini models, and the way you do that is this Google Cloud provides this set of tutorials or this set of walkthroughs, and they're in the form of documentation, so you can go through them. I think it's probably the best way to start with Vertex AI and the models around it.
Okay, thank you, Imran.
Yeah.
Yeah.